Okay, the next invited speaker who is James Tuite from United Kingdom. He works at Open University and his research concerns with uh, general position sets in graphs, right?
Correct. Thank
And
you.
as I remember, the last time we met each other in Moscow, yes, at the conference of graph theory in 2019. You
Yeah,
remember, yes?
Olga Prudny. Yes, it's a shame that traveling there is a little more complicated nowadays. But I hope that things will improve and I'll be able to visit you in Novosibirsk someday.
Well, anyway, James, thank you so much for accepting the invitation.
Thank you.
We are really glad to meet you.
Nice to be here. I presume we need to wait for a couple of minutes as we're ahead of time.
Yes, if you agree, we can start after 2 minutes.
Excuse the chaos behind me. We've only moved in here 4 days ago. So still blank shelves.
Okay, James, we are looking forward to listening to you.
Okay, thank you very much. Let me make this full screen. Но сначала несколько слов на русском языке. Спасибо всем организаторам и особенно Хамиду за то, что пригласили меня сюда. Жаль, конечно, что политика сейчас разделяет наши страны, но мне очень приятно, что математика всех нас объединяет вместе. Ну, дальше по-английски. Okay, so.
Нам тоже очень приятно.
Спасибо. Okay, so today I'm going to carry on with Dorita's theme, talking about general position. This presentation is joint work with lots of people. Tim, I need to fit on the slide, including Dorita, Sandy Klavshar, who's here today, and Aditi Krishnakumar, who I think will be here a little later. But you'll see the full list of co-authors and the last slide when I give you some references. Now, to make this full screen, I need to... There we go. All right. Okay, Dorita's already done the hard work of defining what a general position set is, so thank you to Dorita. So I'll briefly go over the background again. Maybe there are some people who have just joined. But the general position problem for graphs originated as a chessboard puzzle by a famous English puzzle setter called Doudny. And he asked how many pawns we can fit on an n by n chessboard if we require that no three of them lie on a straight line in the plane. And that turns out to be a very deep geometrical question, which was later generalized to the setting of graph theory by some people that I will show in a moment. But as Dorota said, we can also think of this in terms of robotic communication. We can suppose that there are a collection of robots stationed on the nodes of our graph, and they're all trying to talk to each other by sending signals between each other along shortest paths. And to keep communication free, we want to avoid a robot standing on a shortest path between a pair of different robots. So we can see this in this AI-generated picture here. The robot on the left is trying to speak to the robot on the right, but the robot in the middle is getting in the way, and that is what we wish to avoid. So, technical definition, a subset S is going to be in general position if any vertices U and V in our set, and any shortest UV path, then there is no third element of S on that shortest path. And then the general position number, as Dorota said, is the largest number of vertices that we can find in such a general position set. Now, it's known that finding the general position number is MB hard, which is good because it makes an interesting problem for us. What's known about this problem? Well, it's been investigated on lots of different graph classes, and there are lots of different variants, some of which we'll talk about today. Others include monophonic position, which is when instead of looking at shortest paths, we look at induced paths, and also mutual visibility, which Dorota has already introduced. So these are a couple of people of interest in this problem who introduced the problem to graph theory. Here's Sandy, who's giving us a wave now, who introduced this with Paul Manuel, and also Ulas Chandran, who introduced it under the name geodesic irredundant sets independently with Parthasarathi. Okay, let's look at an example. Here's the famous Peterson graph, and here is the largest possible general position set, the red vertices. And this is in, well, of course, it's the Peterson graph, so it's got diameter 2. And between any pair of vertices, if we look at the shortest path between them, there's not another red vertex on that path. If you can see my cursor, then, for example, if we look at these two red vertices and the unique shortest path between them, the vertex in the middle is not red. Let's see more examples. This is slightly more exotic. The Klebsch graph, and this forms our largest general position set here, or GP set. Of course, this is a little harder to verify. We did this by computer. But if we look at any pair of red vertices and any shortest path between them, there is no third red vertex on that path. And here's the Frucht graph, an asymmetric graph, a little bit harder to work with. And the general position number here is 5. Again, if we look at any shortest path, for example, between these two red vertices, here's a shortest path of length 3 that has no further red vertices on there. So the general position number of this graph is 5. Let's do some audience participation at this point. Here are some graphs which are familiar to all of us. We've got a K5, a 5-cycle, and a tree. If I can see the chat, then let's see if anybody can, apart from Sandy, of course, or Dorota, because you already know, what would be the general position number then of K5, of the 5-cycle, and of this tree? Any informed guesses? So Shahin says for K5 it would be 3. Could we do any more than 3? Well, I'll reveal the answer for K5. For well, 4's more. 4's also correct. In fact, we can do 5 for, oh yes, thank you, Timothy. For K5, it would be 5 because in a clique, we can select every single vertex. Why? Because the shortest path between any pair of vertices is just length 1, and so there can't be another red vertex in between them. So that gives us an important lower bound on the problem. The general position number, and it's also the mutual visibility number, is bounded below by the clique number of the graph. You can just take all the vertices of the largest clique. Okay, what about the 5 cycle? Uh, 2 is good. We can go one more. Yep, it'll be 3. If we take the top vertex and the 2 lower one, that will work. And lastly, the tree. I can see Timofey is getting good at this. Or again, we can do more than 2. Okay, time to reveal the answers. Here are largest general position sets. So in the clique, we've got all of them. We've got 3 on the 5 cycle. And it turns out in a tree, the best you can do is always to take all of the leaves. Okay, let's continue. Now we've had that short practical introduction. Why am I talking about this subject at all in a meeting on domination? There are, as Dorota said, some connections between the 2 subjects. One simple connection is that if you sum the general position number and the domination number, that's bounded above by the order of the graph plus 1. And it's not difficult to show that you can meet that bound only for complete graphs. That's the only obvious formal connection I know of, but a more important connection is how the 2 subjects have related to each other. Of course, they both belong to what's in the MSc classification called special subsets, and domination sets are probably the most developed subject in that area. So in developing the general position problem further, what I'm aiming to do, and perhaps how other people think as well, is to see what's of interest in the domination problem and try and translate that into the general position problem. Of course, sometimes that works, sometimes it doesn't. So in this talk, we're going to see some of the ways in which the domination problem has impacted the general position problem. And then towards the end of the talk, we're going to see how the general position problem is repaying the debt and contributing to the domination problem. So let's make a start. Let's talk about colorings first of all. Now, the domatic number is a very important area of domination theory. That is the largest number of colors we need in a vertex coloring, such that each color class is a dominating set. So we can ask the same thing about general position colorings. The general position chromatic number of a graph is defined to be the smallest number of colors needed to color the vertex set, such that every color class is in general position. Let's see an example. Let's go back to the Peterson graph. The red vertices are the general position set that we saw before, and the blue vertices are another maximal, in this case, general position set. And so we see that we can cover the whole graph using just 2 colors, and that's best possible in this case. We can get some simple bounds for this. For example, each color class can contain at most GP of G different vertices, and so a lower bound is just n divided by the general position number. And if we color them greedily, say we take a largest general position set and make that red, and then in the worst possible case, we can divide the remaining vertices into color classes of size 2. So that gives us the upper bound here. And there's a lower bound in terms of the diameter as well, because any longest geodesic has the property that no 3 vertices on it can have the same color. Otherwise, we'd have 3 in a line. And so we need at least the diameter plus 1 divided by 2 colors. It turns out that diameter lower bound is tight for block graphs, and you can show that by induction. Also, if we have an isometric subgraph, H of G, then the GP chromatic number of G is bounded below by the GP chromatic number of H. Okay, let's look at some simple results. If we look at a graph with general position number 2, that's the same as a path or a 4 cycle, then dividing the vertices into sets of size 2 is the best we can do. And so the GP chromatic number is just n over 2. And for cycles of length not equal to 4, we can divide it into 3s as well. So that gives us n over 3. More interestingly, an upper bound on this chromatic number is given by the clique cover number. So you could say that is the number of colors that you need to color the graph such that each color class is a clique. As I said, each clique will be in general position, and so that automatically gives us a general position coloring. However, the two numbers aren't tied together because for any pair A less than or equal to B, you can find a graph with general position chromatic number A and clique cover number B. For a graph with diameter at most 3, I see there's something on the chat. Let me just check if there's any. So for trees, the lower bound is the diameter over 2. Well, the diameter plus 1 over 2, that's a lower bound. Yeah, normally you won't have equality because you could just take lots of leaves. But that's tight, for example, for paths. Oh, so you mean for the GP chromatic number, the lower bound? Yeah, then the answer would be exactly the ceiling of the diameter plus 1 divided by 2. So basically for a tree, you would color all the leaves red, take those off of the tree, then color the remaining leaves, get rid of them, and so on. So it's an inductive process, shaping off the leaves. Okay, so for a graph with diameter 3, any independent set will be in general position, because if you try and draw a shortest path which contains 3 of them, that would have to have length 4, and I've just set the diameters at most 3, so that doesn't work. So it follows that any proper coloring will also be a general position coloring, and so the GP chromatic number would be bounded above by the chromatic number. And we can actually improve that slightly to something called the co-chromatic number, which is not quite so familiar to everybody, but that is a coloring in which each color class is either an independent set or a clique. But the difference between them can be arbitrarily large. For example, you can take the join of a single vertex with k copies of k cliques. Okay, some other results. What about in terms of size? The largest size, that is number of edges of a graph with order n and GP chromatic number A, is at least n choose 2 minus this cubic in A for n large enough. And the construction works by deleting a disjoint union of cliques, one of size 2, one of size 3, sorry, one of order 2, order 3 up to order A. And it's not difficult to confirm that you can do that with A colors. I don't know if this is best possible, and it would be very interesting to find out if it is. But the lesson is that you can have, asymptotically speaking, almost all edges present in a graph with given GP chromatic number. This is also an MP complete problem. In fact, it's MP complete to decide if a graph with diameter of just 2 has a GP coloring with at most 3 colors. You can reduce that to 3 sat. So this is intrinsically an extremely difficult problem. Let's look at some different families of graphs. For complete multipartite graphs, it just reduces to the co-chromatic number that I just mentioned, and there's a nice formula for that. For a Kneser graph, that is the graph with vertex subset formed by the 2 subsets of some alphabet of size n, and then we draw an edge between 2 of these subsets if they're disjoint. It turns out that n minus 3 is best possible for that, and you can show that by induction. because for large enough n, you can show that one of the color classes has got to be an independent set, which by the Akademgorodok theorem has size at most n-1. Then you can recolor some of the vertices to make that independent set maximal, take that out, and then we're left with a smaller Kneser graph and apply induction. Now it gets very interesting when we start thinking about line graphs of complete graphs. It is known that, let me do some drawing, a general position set, well, firstly, in the line graph of the complete graph, we can picture the vertices of that as the edges of the complete graph. And it is known that the general position sets in that graph correspond to unions of, oh, I appear to be in blue rather than red, but never mind. They're unions of triangles, as many as you like, with stars. Again, we're picturing these as edges inside the complete graph. So we could have a single edge and a P2, these are kind of trivial stars, but this would be a general position set inside the clique. And the largest that we can possibly do, if n happens to be divisible by 3, is n by splitting up the vertex set into triangles, and n-1 otherwise. When you can't do that, and you could just take one big star that touches every single vertex. So when we come to think about coloring all of the vertices of the line graph of the complete graph, the question arises, can we decompose the graph into collections of triangles? And this is connected with Steiner triple systems. In fact, resolvable Steiner triple systems. Can we decompose the edges of the complete graph into collections of Steiner triple systems? That's also known as a Kirkman triple system, and it turns out that these exist exactly when n is congruent to 3 mod 6. And this gives you the n-1/2 here. You can also alter that a little bit and take into account parity considerations, and you get all of these answers. But where it gets really interesting is when n is congruent to 0 mod 6. In that case, we got the lower bound of n/2, but the existence of the right coloring followed from something called a nearly Kirkman triple system, which I hadn't heard of before doing this work, which is a decomposition into lots of Steiner triple systems and then one bit left over. And these always exist for n divisible by 6. So let me get rid of my annotations now. Carry on. Okay, but I especially want to bring out the connection with domination. If a graph is diamond-free, then this GP chromatic number is bounded above by the total domination number. Why is that? Well, suppose you've got a vertex and look at its neighborhood. And I claim that we can color all of these red. And that will be a general position set. Why? Because if we had a shortest path that includes 3 of these neighbors, then that would form a diamond, which we've ruled out. Okay, so in a diamond-free graph, any vertex neighborhood will be a general position set. And so we can just take a collection of open neighborhoods that covers the vertex set. In other words, we're using the total domination number. In fact, for mutual visibility colorings, you can imagine how that's defined. The same bound holds without assuming that the graph is diamond-free. Again, these two numbers are not tied together. We can find a diamond-free graph with GP chromatic number A and total domination number B whenever A is less than or equal to B. And you can prove that using spider graphs. This bound turns out to be pretty useful in some scenarios. For example, for a large grid, it, asymptotically speaking, gives the best possible answer. by dividing it into fours. You can see the kind of pattern that we're using here. And there are some leftover vertices. And if you're careful about how you color them, you can improve the bound slightly. But this upper bound here is just the total domination number of large grids. I'd like to, in this moment, to also mention some other connections with domination. There was a paper that appeared maybe just 2 weeks ago called Distance Mutual Visibility Coloring, Relations with Total Domination, Exact Distance Graphs and Graph Products, by people including Aparna Lakshmanan, who I think might be here, Boston Brescia and others. And they proved that here, the chi mu k is the mu k is referring to a mutual visibility set such that all of the vertices in the set are at distance at most k apart. And then the chi is a coloring in which each color class has that property. And the gamma k here is a dominating set, no, not necessarily dominating set, a set with the property that any vertex is at distance at most k away from a vertex of that set. And they proved this nice inequality here. And also, if the graph has girth at least 7, then chi mu 2 is bounded below by the domination number. And also, if G has no isolated vertices, then chi mu 2 is bounded above by the total domination number, which is rather similar to our result, but independent. So these are all very interesting results. And I wonder, can we characterize the equality cases in any of the things we've just spoken about? I don't know. I think that's an interesting direction to pursue. Okay, enough of coloring for now. Now let's talk about games. What's the inspiration? In the domination game, there are 2 players called Dominator and Staller, and they play a game on the graph by selecting one vertex at a time, and the game stops when they've formed a dominating set. And then we want to measure the size of this dominating set. However, Dominator and Staller have opposite goals. Dominator is trying to keep that set small, while Staller is trying to make the set large. In other words, to make the game carry on as long as possible. That's got a very big literature, and there's been some very nice progress on the domination games recently, for example, by Julien Portier and Leo Versteren in Cambridge, proves some excellent bounds. But for our purposes, the importance of that is that it inspired us to look at the general position games. So I notice here I've got the word chromatic on that slide, forget that, general position games. So here we have 2 players who we call builder and blocker, who take turns to select new vertices, such that the set of selected vertices is always in general position. The goal of builder is to try to make the set as large as possible, while blocker is trying to keep the set as small as possible. So what's the number of vertices that we get in the resulting set? Well, one thing I have not specified here, and we'll speak more about this later, is who starts the game. If builder starts the game, then we call that the game general position number, denote that by GPG of G. If blocker starts the game, we call that the B dash game, and then include a dash in this GPG. Now, both of these sizes of sets, GPG and GPG dash, that's the number of vertices in the resulting set under optimal play. Both of those will obviously be bounded above by the general position number, and they will also be bounded below by something we call the lower general position number, which is the number of vertices in a smallest maximal general position set. This the lower general position number was also inspired by domination theory, where you have the upper domination number. So it's like a worst possible choice. So this game invariant is a way of studying what you could call typical sets, which are like between the 2 extremes. Okay, let's look at an example. Here I've got a complete 3-partite graph 4 blue vertices, 2 red, 2 green. So let's play a quick game and see how it works. So here, if I am builder, I could go here first, and at this point blocker has a choice. If blocker chooses another red vertex, then we've got to complete the game solely using the blue vertices, and we'd get 4 as the result. So that's not the best that blocker could do. Blocker could instead choose a green vertex, and in this case, all that builder can now do is complete a clique using different colors, so we'd have to choose this red vertex here. Alternatively, if blocker starts, they'd probably want to go inside a small color class, let's say this red one. Then builder can choose whether he wants to complete the game inside that independent set or whether to use all different colors. So in this case, it's best for him to choose a blue vertex, and then blocker has to reply with the green vertex. Okay, as a result, we get these formulas for the complete multipartite graphs, and that has the useful consequence that we can characterize the triples of values of the general position number, the game general position number, and the lower general position number. So basically all feasible triples are actually possible. For Knaser graphs, the game general position number coincides with the lower general position number, so it's not always in between the two extremes. It turns out that the answer is 6. We characterized as well trees with, sorry, not trees necessarily, all graphs with GPG dash. So this is the blocker starting first, equal to 2. And it turns out that this holds, that the B dash general position number is equal to 2 if and only if the graph looks like this. What we don't know exactly is when the game general position number, when builder starts, is equal to 2. That's a little bit more tricky. Okay, I said that I would speak further about the issue of who goes first. Now, in the domination game, there's something called the imagination strategy, which is basically strategy stealing, if I remember correctly, that shows that where the dominator or staller goes first makes a difference of at most 1 vertex to the result. So we imagined that a similar result would hold in general position games. This turns out to be completely false. So in one direction, whenever A is less than or equal to B, one can find a graph with game general position number A, and with builder general position number A and blocker general position number B. And you can just use the complete apartite graph with each part of size B using the theorems we've just seen. Looking at small examples, it feels like it's easier to have the inequality in this direction with the builder number less than the blocker number. In short, that going first is a disadvantage because then the next player can react to what you've done. So we were stuck for a little while on whether the inequality can be in the opposite direction with the blocker number smaller. And it turns out that it can. Why? Well, suppose that builder goes down here. It turns out this is the best possible starting point. Notice here that we've got a collection of 4 cycles all glued along an edge and a collection of triangles. And there are 5 triangles here. In fact, it's very important, as we'll see in a moment, that the number of triangles here is odd. Why is that important? Because at this point, red, who's representing the builder, he can regain the initiative because eventually blue, who's the blocker, is going to have to go somewhere else in the graph because we can have red here, blue, red, and eventually blue, the blocker, will have to go somewhere else. Let's say at x1 here. It can't go at x because that would form 3 in a line. And at this point, red can reply by taking x2 and then the rest of the game has got to proceed like this, and you end up with a large general position set. What about if blue on his first turn did not go in one of the W's, but instead went to X? In that case, red could reply with Y1 up here, and then the rest of the game would have to proceed like this, and you still get a large general position set. Okay, and well, you've got to work through all the scenarios. Okay, what about when the blocker goes first? What's the best that blocker can do now? Well, if red, the builder, goes to X, then blocker can reply with Y, and you get a triangle. You can't add anything else, and the game's over. So that would be a bad choice for builder for his first move. So suppose instead that builder went inside the vertices labeled W here. Again, the blocker can now force builder to go somewhere else in the graph eventually. Let's say it goes to X1, and then blocker can reply with Y1, and again, the game is over, and we've got a relatively small general position set. And so this, if we allow many more 4 cycles and triangles, this gives us a graph in which the game number, the builder number, is smaller. So this raised a question for which pairs A, B is there a graph with builder number A and blocker number B. The question was open for A strictly more than B and B even. And in the paper, we managed to find constructions for some of those, but not all. But this direction was finally completed by my student Isha Evans, who, using some very nice game theory, proved that all feasible pairs are realizable. For trees, for the blocker number, an upper bound is the leaf number minus the maximum degree plus 2. And the reason for this is as follows. If you take, if this is blocker's first move, then builder will have to go inside one of the components resulting from that vertex being deleted, and then all of the rest of the game has got to take place inside that component, because if we had something elsewhere, we'd have a shortest path like this. And we've said that the general position number of a tree is the number of leaves, and if we look at this subtree, if we include this base vertex, that subtree would have exactly this number of leaves, or at most that number of leaves. And we've characterized equality, and it turns out to be a certain family of caterpillars. Okay, now let's start talking about how the general position problem is given back to domination. I'm going to explain to you about what we call the mobile general position problem. This was inspired by, in Milton Keynes, we have mobile delivery robots, which run around and bring groceries to people. It's very neat, nice to watch them running around. And during the pandemic, when we had very little to do, it occurred to me, watching these robots, that our robotic picture of the general position problem is lacking one important feature, and that is movement. In the real world, these robots may have to move around the network at the same time as communicating with each other. So this inspired the following problem. We have a configuration of robots on the nodes of a graph, at most 1 per robot. And at each stage, a robot can move to an adjacent unoccupied vertex, 1 at a time. And we denote it by this symbol here, U squiggle V. We require that at each stage of this process, the set of robots stay in general position, so they've still got free communication, and that every vertex must be visited by a robot. So we could imagine that the robots are delivering groceries, And that means that the robots can always speak to each other freely, but they can also visit every house and deliver the groceries. The question then is, how many robots could we have in such a configuration? The largest number of such robots we call the mobile general position number. And it's trivial that this lies somewhere between 2 and the general position number. Okay, let's see an example. If we look at C5, 3 will work. We can't initially move this robot. If we try to move it down here, we would get 3 in a line. However, we can move this robot here, say, and then we would have a configuration consisting of these 3 vertices. And then by repeating that process, essentially, we're rotating the set around the vertices, and we can visit everywhere and always stay in general position. For C6, this is a little bit peculiar, because if we take 3 vertices, in this case, we can't make any moves. Why? Well, suppose this robot moves here, then we would have this shortest path. So in this case, the mobile general position number is not equal to the general position number. But for every other cycle of length 6, we have equality. So the mobile general position number Kn, that will just be n. We can start with a robot everywhere. Automatically, everything is visited. For cycles, I say it's normally 3. For a block graph, it turns out we have equality with the clique number. You just start with robots at the clique and then send them out to visit the other places and bring them back. Slightly less simple results. In a complete multipartite graph, the answer is the maximum of 2 or the number of parts minus 1. And again, this allows us to compare the mobile general position number and the general position number. And we have this nice bound on unicyclic graphs as well, something that I studied further with Dorota, actually, in a recent paper. Another example of Peterson graph, if we try and start with the largest general position set, we can't move anywhere. Every robot is bound to its place. If we take just 5, we have something like this. And in fact, all that can happen now is this robot moves back and forth along this edge. Not very interesting, and we can't visit everything. But if we go down to these 4 vertices, it now works. For example, the green one can go down here and back. This one can go here and back. This can go here and back. Red can go up here and back. And in short, we can visit everything with 4 vertices. More generally, for Kneser graphs, of which the Peterson graph is an example, there are just 3 types of general position sets that we need to consider. And it turns out that the mobile general position number is given by the maximum of 4, or essentially the clique number minus 2. Gives you just enough flexibility to do this. In line graphs of complete graphs, the answer is n minus 2. It turns out that if you are very near to the general position number, everything's rigid and you can't move. But if you use a star with 1 edge missing, so it's nearly spanning, then you have just enough flexibility to visit everything. And now, if we just change pace slightly, let's talk about completely mobile general position sets. This is where we have an extra condition. Let's go back to the robots delivering groceries. We may also require, quite naturally, that every robot can visit every house. Otherwise, you may put the groceries in 1 robot and you find that actually you can't go to the correct destination. So we call the robots completely mobile if they are a mobile general position set, but also every robot can visit every vertex. So you see the difference? In the first version, every vertex could be visited by a robot, and now we require that every vertex can be visited by every robot. And we denote this by mob GP star. So it's obvious that mob GP star is bounded above by mob GP. And when we were first working on this problem on paper, we actually couldn't find any graphs which had a difference greater than 1. And this is where my student Ethan Shallcross comes up because in just the first week of his internship with me, he found graphs which have a much larger gap. And these are actually the same as what are called half graphs. And let's see why these have a large gap between these two versions. Now, the important thing here is that if we have 3 or more robots, we can't have this situation where we have a robot on the top left and one on the bottom right. Because now whenever we try and add in another robot, we'll get 3 in a line. So we can have a mobile general position set like this, and we just move one at a time upwards like this, and that's fine, everything's visited. But this configuration isn't completely mobile. Why? Well, if it's completely mobile, then at some point, 2 robots are going to need to switch positions. So let's suppose R1 is the one most to the left, and R2 is going to need to move to the left to visit the vertices over there. Well, let's look at the moment when that switch happens. Now, we've already said that if we have 3 or more robots, then we can't have this situation. So at the moment of the switch, the robots have got to look something like this. But then when R2 moves to the left, again, we'll create that forbidden configuration. So it turns out that if we want a completely mobile configuration of robots, 2 is the best we can do here. And so we can have as large a gap as we like. If we want to determine exactly which pairs of numbers we can just change the graph a little bit, and that gives us the needed theorem. It also has a nice relation to the clique number. I think for time I won't actually do the proof with you, but this is bounded below essentially by 1 plus the clique number divided by the diameter. And that implies that the Erdős-Rényi random graph is going to have both general position and mobile general position number of order about log n, interestingly. That bound is also tight if we look at fixed diameter, but interestingly, if we fix the clique number and allow the diameter to increase, that is not tight, we can improve it slightly. So if the clique number is at least 5, you can show that there is a mobile general position set of order at least 3, and that gives us an upper bound on the number of edges that a graph with mobile general position number 2 can contain. So an upper bound is the number of edges in the Turan graph, the 4-partite Turan graph, but we conjecture that actually the graph with the largest number of edges subject to this condition is actually the 3-partite Turan graph. And we don't know why there's this difference. Strangely, we can even find such graphs with K5 minus, so you can be very, very close to having a 5 clique. So this is very strange, and we will continue investigating this. Okay, now that we've defined that problem, another way that the domination problem has influenced the general position number is security. There's something called the secure and co-secure domination problems, which have already come up in the first talk, in fact. So for example, a dominating set is secure if for any vertex outside D, there's a vertex inside the set that can move to it and still have a dominating set. And this led us to define a secure general position set as one in which for every vertex outside the set, there's a robot inside the set that can move to it and still be in general position. And it's co-secure if every vertex inside the set can make some move. So these are just translating security and co-security from domination into general position. And this was interesting as well because it's like a simpler version of the mobile problem I just defined to you. In particular, we hoped that we could get an angle on the complexity here, because the complexity of the mobile general position problem is completely unknown. It was proved by others, including Dorota, that the mobile mutual visibility problem is NP hard, but we don't know about the mobile general position number. So what can we tell via security? In particular, notice that a secure general position set, because it can visit everything, that's automatically a mobile general position set. And so the secure general position number will be bounded above by the mobile number. But because we've got to be able to reach everything, it's also lower bounded by the domination number. So that's a nice connection between the two. In particular, if we have a graph with mobile general position number less than the domination number, we can't have a secure general position set. There's no guarantee that such a set exists, unlike the domination version. Now, we do know that the co-secure problem is NP complete, and you can show that using, if you take any graph and take the join of a Kn, then the co-secure number, that would be n plus the clique number g minus 1. So we can reduce it to the clique problem. But we still, in fact, don't know the complexity of the secure general position number. One interesting inequality is that the secure general position number is bounded above by the co-secure number plus 1, which is slightly unexpected. This raises the question of when does a secure general position set exist? Any such set has got to be both in general position and dominating. So that suggests looking at sets that have both of those properties. In particular, it follows from this that no two vertices of a secure general position set can be at distance 4 or more apart. And in particular, any graph with diameter at least 6 cannot have a secure general position set. Now, how is it giving back? So in our last few minutes, I'll describe a mobile version of the domination problem. So now, again, please imagine robots stationed on the vertices of your graph, but now we want them to be a dominating set. At each stage, a robot will move to a neighboring unoccupied vertex. We want the robots to always be a dominating set, and we want them to be able to visit every vertex of the graph. Subject to that, we want to have the smallest possible number of robots. Now, this number, which I'm denoting by mob gamma, because it's a dominating set, obviously this is bounded below by the domination number, and it will be bounded above by gamma 2, by which I mean, and this is slightly different notation to the first talk, this is the number of vertices you need such that every vertex is dominated by at least 2 elements of the set, because then the second vertex can just move in to that vertex and everything gets visited. And it's known that's bounded above by the domination number plus the independence number. One trick you can do in order to make this work is to start with a dominating set. Let's say I draw this in red. And suppose that when you delete that set from your graph, you're left with some collection of components. You can just station one robot in each of these, and that can visit all of the remaining vertices of that component. And because we always have our robot stationed here, this will always be a dominating set. So they'll be bounded above by the size of that dominating set plus the number of components it splits that graph into when you delete it. In that way, it's perhaps difficult to have a graph with a large mobile domination number, but that's just a little trick. Using that, you can deduce these values for cycles and paths. So you can see that normally the two values coincide, and sometimes you need to add 1. And here for complete multipartite graphs as well. A more interesting lower bound is that the mobile domination number is bounded below by the leaf number, of the graph. And the reason is that if you have a vertex, call it U, with R leaves, you've always got to have at least R robots inside the set U plus its leaves. Because if at any stage there are R minus 1 robots in there, then there's got to be a robot at U in order to dominate all of the leaves. But then this robot R can't make any legal move because however it moves, there'll be something which is not dominated, and so it never gets to visit those two empty leaves. We could also think about the completely mobile version of this problem, in which we want it always to be a dominating set, but we also want that every robot can visit every vertex. And it turns out, well, firstly, it's not known that every graph has such a set at all. But if it's two edge connected, then we always have a completely mobile dominating set. And the number of vertices in that graph in that set is bounded above by n minus the minimum degree. Why? Well, if you take n minus delta robots, those have automatically got to be a dominating set. And all that we need to show is that a robot at some vertex u can move to any neighbor u dash of u. Now, because we're assuming the graph is two edge connected, u dash has got to lie in a cycle, and we can create the needed movement as follows. So let's say here we've got u, and here we've got u dash, and let's say we've got some unoccupied vertex, maybe on the cycle, maybe not, and this is the shortest path. We can first shunt robots along this path until we get a robot here and get an unoccupied space on the cycle here, and then we shift all the robots around the cycle, and the robot at u will then move to u dash. And then because the graph is connected, being able to move from u to u dash is sufficient for every robot to be able to visit every vertex. And there's also a nice connection with eternal domination, which again we briefly mentioned before, when a dominating set has got to be able to react to any attack on the vertices of the graph. And it's easy to see that the mobile domination number will be bounded above by the eternal domination number. But the two numbers are again not tied. You can show that for any r less than or equal to s, there's a graph with mobile domination number r and eternal domination number s. So the mobile domination is, in a way, a relaxation of the eternal domination number. And while writing these slides, it occurred to me actually that we can have a stronger upper bound than the eternal domination number. We can instead replace it by the secure domination number. Okay, just to round off then, I'll indicate some other directions in which domination has influenced general position. Well, there are the domination polynomials, and it's a very important subject there when these polynomials are log concave, and that inspired us to write about general position polynomials and see what properties they have. Independent domination inspired independent general position. There's just one paper on that, so there's a lot to be done there as well. And fractional domination suggested to us looking at fractional general position, and it turned out that that had already been done in a different context, but that's a very interesting problem as well. For any more information on any of these topics, we have a survey paper on the general position problem, and let me give you my references as well to the three subjects we've looked at here: the mobile problem, the coloring problem, and the secure problem. So thank you everybody for your time and attention. Спасибо всем за внимание.
Thank you so much, James, for your wonderful presentation. Any question? Any questions?
Can we study Nordaus-Gaddam type inequalities? Absolutely. Indeed, that was an open question at the end of our paper. So I think that needs doing. Nordhaus-Gaddam type inequalities are also very interesting for the coloring problem. And we conjecture that the standard Nordhaus-Gaddam inequalities for the chromatic number can actually just be replaced by our GP chromatic number, which is interesting. So in the standard Nordhaus-Gaddam inequalities, we can assume that the color classes are in general position. We don't have a proof, but it looks like it may be true, and that's an interesting variation on the problem.
Okay, other questions? Okay, James, thanks again. We're looking forward to meeting you at some point in the future.